So in today's session that we will try to see already in a past systems or already if you have some kind of a material libraries that which are already developed that's available with a different version of Navitas or with a different machine. Let's say, for example, that you have saved all your materials information in your lab and you want to bring that information, material information to your laptop for your multiple iterations and restudy of those things and all. In that particular case, also how we are going to use this. That's a challenge, right? So that overcome that we will see now. So let me go here. I've downloaded this particular two files. Let me copy these two particular files. I'm just copying it. Just go Control C and go to here like in this PC and go to C drive. Inside the C drive that you have to go for users. So here I'm a user like a HP. So I'll just go inside my username. And then here, like I just need to see Abacus plugins. There is a folder called as an Abacus plugins. So just go inside this and Abacus plugins. Now here you can see it's a material lab info library. So here I'm just going to paste the other two libraries also. One is a hyperelastic, completely related with rubbers, and the other one is a material databases. Normally I have it. Okay, so these two are the files that I have it. Now I'm just closing it. Now when I just try to go or something, whatever it may be, I can't see anything over here. I can't see anything over here. Just try to close this in that particular cases and reopen the Abacus. Try to close this and try to reopen this Abacus. Then automatically you can able to see like what's a number of things that you can able to see, all those things that you can. Going for this and going for the property module here. Now in the material libraries, here I have an hyperelastic and here I have a material databases, right? So when I click on this material databases, now you can see this. I have a metals, I have a plastics, I have a cables, like some other things and all it is there. These are some of the other materials that which it is there. So with all the standards, it is available. Like a 1.4307 is one of the materials. SS304 is a kind of a stainless steel. PTFE is a kind of a rubber. O-rings are like a rubber. So foam material I have. Berlin is a kind of a plastics. So and inside this, I have some concrete materials and steel materials are there. Aluminum materials are there. So you can able to call up all these particular materials. This is my set of libraries, guys. This is my personal asset. So I'm not sharing this with you. So you can start building off your own materials. If any one material is suitable for your project, if you feel, then I'll try to share that particular material along with you. Okay, now out of all these things, if I would like to pull this SS304, like it's a stainless steel, I would like to pull. So now you just click on this add material to your current model. Then in this, you can see this SS304L. Once you click on this, then you can see it's a density, elastic, and plastic. So in the plastic, it's all like it's a true yield stress and true plastic strain values. Even in our last classes that we have seen about the formulas also to convert those particular things and all for the true stress and true strains. It's as simple as like you can type the formulas also. True stress formula if you can type. And you just go for the images. Here you can see this is where it is now. It's a true stress is equals to engineering stress into multiplied with 1 plus engineering strain. So this gives you the true stress value, whereas the true strain value is this. So let me, this is where actually the true strain and true stress values and all. So true strain is equals to logarithmic function of 1 plus engineering strain. So these are the values that is available. Let me share you this particular screenshot. So remember this, whenever you are just trying to feed your engineering stress and engineering values, then this is actually that you have to feed these particular values. Okay, so this is how that you need to convert this. And in the last class, I think in the chart window, I have shared you about the web digitizer. I've shared you about the web digitizer also. So it's a web digitizer is something that which helpful for you to convert any kind of engineering stress strain graphs or any graphs that you have it, you can able to convert that to your data as what we have seen over here, as what we have seen here. So like this, you can able to convert those things. Dennis, hope you remember that, right? In the last class that we have discussed it.
Yes, by using the graph, we can collect.
Yeah, web plot digitizer is there, and I have shared you those link also. Again, if I want, I can just share you those links. That's a web plot digitizer. If you just go to this, this is what your web plot digitizer. If you just go. So this is a web plot digitizer. Once you just click on this, then automatically done. So now you have to load your image and choose your images. So let's say on the desktops that I have something. Sorry, I have deleted that, I think. I didn't have any images. Like if you have any data sheets, that information you have, like you can. So I think, Ashish, if you go through my video in the last video, that you'll come to know how to convert that. That's very, very important, guys. Many of the students don't know. Many of the industrialists, they don't know how to convert these particular things, and they'll break their heads and they'll write Python code or something, blah, blah, and blah. That much depth is not required. It's already available. An online converter is already available. So you can use that particular converter, and this is where actually. So this helps to convert the image values to tabulated values. Okay, you can use that. Next, come back to because again, guys. So, and then actually, in the last thing that we have seen some of the options, like when I just go and let me open this particular presentation. Yeah, Omnish is there now. So this is where the unit systems that you are following it. So you have to must and go for this particular unit system. Okay. So in the last things, when I just go over here, whether I have saved that particular program or not, I'm not sure. That's on 25th, I think we have not shared. Any temporary where I have kept it. Okay. This one. Okay, I've not kept anywhere. I think in the last problem that we lost it, no problem. Again, we try to solve it back. There's only an I section. I didn't save that problem actually. Last week I had a power issue and think that's a problem. The videos are also not updated. Okay, let me go on and we try to solve this as we use the same folder, but we try to rename this again. So renaming this as a 02102021. I'll use this particular thing as my working directory. And then today in overall problem, I try to explain you one small example. It's a very small example, like it's a cantilever beam or a simply supported beam, you can consider it. And I'm trying to apply some kind of a force on it. And because of the force, how the beam is reacting, that we will see it. And with that, we will try to know all the components available inside. Maybe for the Dennis, it's a kind of a revision session for you, but without that, last time I had gone in a very fast way, right? So this time I'll go on it deep and then I'll explain you one by one. So I'm going on, with the part module here. So in the part module that I'm just trying to create one particular part. So remember this, guys, please try to correlate each and everything to your problem, because than of me, you know the best about your problem. You have to correlate all the things about your problems. So, and you know how to create all these particular sections, try to build this. I was expecting some kind of a geometries, but you people are sharing me the technical papers. So try to explain, send me up the geometries also. So on Tuesday when we are meeting it, we are going to create Tuesday one geometry, Wednesday one geometry, and Thursday one geometry. We need to create it. And on Friday, we are going to create a material properties for all the geometries. That's what is my target. So come up with all your geometries. So that's where like in the parts I would like to create it. Here I can go create a new part or right click on this and I can click on create also. Either from the model explorer you can go or from the modules icons also you can able to. I'll just name this. It's like a beam analysis. I can just name this as a beam analysis. Sorry. I'm just trying to solve this as a beam analysis. It's a 3D. It's a deformable. And I would like to solve this as a beam. So I would like to use this as a 1D element also. Okay. So now coming on that particular picture, as we were discussing about all these particular things, the initial classes that we have discussed about what is finite element analysis and why we have to use finite element analysis, what is an element and what is a, are these things we have discussed it or not? Please remind me once. You guys there, right?
No, sir, I guess.
Remind me that because it's like a regular topics I used to discuss with many people also. So I may not remember that exactly that we have discussed it or not. If not, then we will try to discuss it now.
Actually, sir, last class we didn't have the LAN thing now, so we were not able. I think so. We haven't taught us about the finite element, like little bit exposure also.
Okay, fine.
Little exposure.
Okay. Let me give you a brief introduction about that first finite element analysis. See, the very first thing, like when I just say something about your names, let's say, like if it's Ashish, it's having some meaning, like it's a Dennis, it's having some meaning, or it's a Omnish, it's having some meaning. So when you just call up with a name, there is some intention behind that, like that power, that kind of a vibrations, or that kind of a feel that you have to give it for this. When you just say it's a success, that gives you positiveness in your mind. And when you just say it's a failure, then you may think about like it's a little lag on that. So like this, everything, like if you talk about a subject, as a structural design, you say. So what's a structured design is, why the topic has been named up with that. Like if you just say it's a fluid mechanics, so studying the behavior of a fluid at various conditions, that's what the fluid mechanics are. So similarly, we have a subject, this is what it's a finite element analysis. It's also why we need to call this as a finite element analysis. Okay. So the best example actually, when you just take some kind of a metallic rod or something like that, that you are taking it, you just assume that like that you have this rod, or like you can just assume like any kind of a rod that you have it. So when you just have this metallic rod in your hand, let's make put you on this. So 3D shapes also I can able to get it somewhere. Yeah. So I have a cylinder like this. I have a cylinder like this. That's a metallic cylinder. Let's say I'm just trying to consider this as something like steel. Okay. I have the same another one over here. Let's say this I'm not considering as a steel, but this I consider this as an aluminum. That's a very common example. Everyone takes it the same. I'm taking it for better understanding. Okay. Now, when I just take this picture of FEM, it's nothing but like finite element analysis. When you just talk about this an FEM of finite element analysis, what it says is we'll divide this particular component. So F is finite, E is an element, and M is like a methods or analysis. You can just call it as a FEA or FEM methods, or you can define this as a methods or an analysis. Okay. So when I talk about this, what's finite actually? Finite is nothing but like which is a countable number. Okay. Why finite comes in picture now? So when I take this particular, either it's a steel or it's an aluminum or whatever it may be, when I just consider this particular any kind of a material it is, whatever be the material it is, it's a combination of, it's a combination. Sorry, just pulling out from the same. Sorry, it's nothing but when I just take it up, this is a combination of some. It's a chemical composition. It's a combination of some chemical compositions. And this chemical compositions is basically from an atoms and molecules. Okay, so when you just say this particular part, either it's a steel or an aluminium to achieve this particular shape or to maintain this, it's a combination of some chemical compositions, and the chemical composition consists of atoms and molecules that you have. Okay, these are the atoms and molecules. And when you just say about this in atoms and molecules, is it possible to count this particular number? How many atoms are there or how many molecules are there? Is it possible to count when I just say it's 1 meter rod I have taken or 10 meter rod I have taken?
Yeah, it's infinite. Like,
okay, so it's always an infinite factors and all. So whatever here we have seen, it's all about like an infinite. So it's all about like always an infinite number. So we don't have any control on that particular aspect. So now somehow, as this is having an infinite number, I would like to bring down this to a countable number. I would like to count this particular infinity to a countable number. So that's where actually what I do, I'll break this positions of my molecules or an atoms, is that right? So I'll just break these particular positions like this. Let's say I have it. I have this have it something like this. Then I can just go. This is where I would like to make this as a copies like this. So this is where I would like to make the copies. This is where I would like to make the copies. Okay, so when I just go here, and this is where I would like to do this one. So this is where like I would like to arrange my elements. I would like to arrange the molecules and atoms in a position such a way that it forms a proper shape, such a way that it forms a proper shape. So in this, what I'm trying to say, this is called a one element. I can call this as one element. If this meeting ends, try to join back on the same link, guys. So this is where it's a no fail, and I can say it's red and go with the red color. So identification is easy. So this is where I can call this as a one element. So all the four borders that we have it, so all the four borders that we have, those things are called as a nodes. So I'm arranging my atoms and molecules in such a position in a disciplined way. I'm arranging all these things and I'm forming one element. So that element is called as an, here that's what the shape that you can see. So we can call this as an element. We can call this as an element. So now elements are of like multiple varieties. Elements are of like a multiple varieties. Like it's there are 1D elements, there are 2D elements and 3D elements and all. So elements are like 1D are there. Sorry, first before going into this and the element shapes that you can see. So when you just talk about the element shapes that we have like wide, which is also called as a hex. Element shapes is a quad, which is also called as a hex, and then we have a tet, which is triangular in shape. Okay, so which is a triangular in shape. This is where actually that we have it for element shapes. Okay, this is where we have it for element shapes. When I just see this one, element shapes again, so what exactly the shapes belongs, and again, there are multiple varieties actually. So let's say here that we have it like this. So we have a 1D elements, 2D elements, and 3D elements. We have a 1D elements, 2D elements, and 3D elements when we just talk about this elements. So you just see this, guys. This is all the material things. It's a chemical composition, atoms and molecules which are infinite in number. I would like to bring down this infinite number to a finite number. So for that, I'm forming an element shape. So this is called as an element that we are calling it by arranging all those things. And if you just talk about the elements here, actually, when you just talk about the elements are of again a multiple types. That's like a quad and a tet mesh. And when you just go again this, we have like a 1D, 2D, and 3D. Okay, so 1D is just a line in shape. 2D is either a quad or a tet triangular shape. The 3D is nothing but it's a quadrilateral or pyramid in shapes and or hexahedral in shapes. Okay, so when I just go for this particular geometries and all, I have to make my some assumptions that when I have to bring my geometries to a 1D, when I have to bring my geometry to a 2D, and when I have to bring my geometry to a 3D. So I have to make this particular assumptions and all. So to make this particular assumptions, that what we can do is you just go and plot your X and Y axis. You just go plot your X and Y, and along with that, you have to plot your Z axis also. So let's say any problem will have these 3 dimensions. Any problem will have these dimensions, right? Any problem will have these particular dimensions. Now, these dimensions talks about your geometry. Okay. Now, with this particular X, Y, and Z, if it is a 1D, 2D, or a 3D, if I would like to represent it, then what I can do from this X, Y, and Z, I just decided one particular factor. So those factors looks like this. If X or Y or Z, which is 2 greater than Y and Z, that means one dimension is 2 greater than the other 2 dimensions, then we can consider this as a 1D elements. Example are beams. Okay, example are beams. Suppose the next thing, if it is X comma Y, is 2 greater when compared with Z, then we can say it's a 2D. Example is plates. Plate elements, which is having a less amount of a thickness. Okay, which is the sheet metal components, we can say. Those kind of things that we can able to form this as a plate elements. And if my X comma Y comma Z both are like more or less approximate equals, like it's not exactly equal, it's an approximate equals, guys. Then we can say it's as a 3D. Example, any solids. Okay, so this is where actually that you can able to bring down your geometry wise. You can able to bring down your geometries, and then you are doing this. And with this, I'm trying to apply my methods or analysis to solve the behavior of it, and then I can calculate the results. So this is where then you can able to check about your results. So this is where from the methods you are calculating about the results. So this is where actually, this is how actually we call this as a finite element analysis, because for any material, it's a combination of the chemical composition, which is having an infinite number. We have to arrange them in a proper disciplined way to achieve one shape, either to achieve an element, and those elements are in the shapes of like a quad or a hex, or hexahedral or a tetrahedral. And these elements also can be in the form of a 1D, 2D, and 3D. Based upon your geometries that you can able to decide when to go with the 1D, when to go with the 2D, when to go with the 3D. And then finally, you can able to apply your methods on it and then getting up the results. This is how actually the thing it goes on for any kind of a program, for any kind of an assumption. This is how it goes on. Do you have any queries in this, guys?
No, sir.
Clear?
No, sir.
Are you learning something new or you already know this?
Knew this, sir.
Sorry?
Yes, sir. It's new to us.
Okay. Please speak out in the classes so that I can recognize that you are listening to me. Otherwise, I'm not seeing your faces, right? So I may get bored after some time. That too, this is on the afternoon sessions. You should be more active. Okay, so that's good then. Yeah. So now coming on this, when I just go over here, when I just say it's a beam analysis, modeling spaces, I'm doing it in 3D only, which is a deformable one. If it's a solid, and I can go, it's a 3D, all XYZ dimensions I need to consider it. When it is a shell, that's a plate element. When it is a wire, it is called as a 1D element. When it is a point, it's just a point. So now I just want to make it as a wire, as a planar element, and it's 200. That if you want, make it as 500 also, and then just give OK. So now I'm just going to create a wire element over here. That's just a line. That means it's just a line. So let me go. Let me go on, put these parallel lines. Which already we have discussed it through. So I'm just going in a very